As we've seen before, a VGA monitor expects certain signals to function correctly. These signals are the horizontal and vertical synchronization signals so that it can generate that scanning pattern for the electron beam. It also expects to see mono, and that mono actually tells me how bright a pixel is. However, we're dealing with colored monitors in here, so what we're going to what we're going to have to do is actually we're going to have to provide the VGA monitor with the red and green and blue signals. These signals are analog signals. They range between 0 to 0.7 volts and tells me how intense in red or green or blue. An FPGA board does not, or an FPGA itself does not provide us with analog signals, so we're going to have to utilize digital to analog converters. And the board we're using currently, which is the Nexus 4, utilizes 3 digital to analog signals, and according to the specs in here, it tells me that these specs are actually they're exactly 4 bits per color. So we're utilizing for the R, the G, and the B, we're utilizing 4 bits in here. So what we're going to be doing from an FPGA perspective is to provide it with an R and a G and a B, which each one of them is a value that is 4 bits. So it's 2 to the power 4. You'll get like 2 to the power 4, 2 to the power 4, 2 to the power 4 for each one of these numbers. And that's what we're going to be doing. So the goal in here is actually to design a synchronization circuit that can actually get the VGA monitor to work. And as it turns out, it's really straightforward and simple. And a synchronization circuit is usually composed of 4 components: a frame counter, a decoding circuit, and a stream control, and some sort of a multiplexer in here. So let's discuss these different components. So the stream control signal is actually so that we can utilize the stream controller, especially the one with the back pressure and the FIFOs. And for the sake of simplicity, and because I'm just trying to get a VGA monitor to work at this point, and we're not creating a whole video system yet, I'm just going to ignore this now, and I just will design a VGA controller that actually just get the basic functionality to work. So it boils down then to a frame counter, a decoding circuit, and that multiplexer. So what does a frame counter do? Well, a frame counter just tells me where I am on the monitor. For example, I do have an X and Y. It just tells me these. And frankly speaking, it will generate these numbers that we've seen on the H-sync and the V-sync. That's basically it. So a frame counter is just 2 modular counters with specific numbers, as we'll see shortly. So these will be provided to a decoding circuit, and a decoding circuit will just tell me where the H-sync is 1 or 0 and where the V-sync is 1 or 0 and where the videos should be on or off. So basically whenever there's a displayable area. So that particular signal will go and feed that particular multiplexer. The multiplexer will only display whatever we put into it as long as the video is on. Other than that, it's basically 0. So it's usually 0 on the frames, basically the borders, or maybe during retrace or something like that. So a simple test would be to connect these signals in here straight to the switches. For example, 4 switches for the R, 4 switches for the green, and 4 switches for the blue. And basically you do that, and you're going to be just basically displaying a single solid color on a VGA monitor. So let's dive deeper into the frame counter first, and then we'll see the decoding circuit and how it's implemented. Again, the frame counter is really straightforward. So let me just explain it here and show you the code. It's generally speaking, it's just a counter that should generate a couple of numbers. One, we're going to call it an HC, which is a horizontal counter, and it's just basically that number between 0 to 799. So it's just basically a modulo 800 number. And the VC, which is the vertical counter, it'll just generate a number between 0 all the way to 524. So it's basically a 525 modular counter. So the frame counter is just basically generating these 2 numbers. And again, just for as a repetition, so a horizontal count and the vertical count, we start at this point. When we start at this point, so the actual number will tell me the pixel location in here. And if you're in the borders, you're going to be basically outside it. Okay, so let's see how this is actually implemented. So if we actually go to Vivado and we take a look at the code in here. So the code tells me here's a frame counter, and we have an Hmax and a Vmax, and we provide them as parameters. They're 640 and 480. They're not exactly the 800 or the 525, but they are parameters. So essentially, or eventually, when we instantiate the frame counter, we're going to modify them because they're parameters. And the reason why we're providing them as parameters is because we might want to build another VGA controller that actually supports different resolutions. But anyhow, so if we go through here, we see the inputs and outputs. We have a clock and a reset. These are straightforward. So the increment is actually just a signal that only enables that counter at a very specific, it's basically an enabled signal. So it allows it to increment. And the reason why we have it is because we want these counters to operate using the clock rate, the pixel clock rate, not the system clock. So they have to operate, I believe it was 25 megahertz. We have some sort of a clearing signal, and then the H count and the V count are actually the count signals. We're going to output them just in case we want to use them later on. Basically, I want the pixel 0 to 0 to have this, pixel 1 1. So I have the actual pixel where I am right now, and we're going to be using them in different modules where we can actually generate certain patterns. And then we have a couple of other signals that are optionals, but that tell me when the frame starts, basically when the X and Y and the H and count and the V count are 0 0, and where it ends, actually the visible frame where it ends and whatnot. Okay, so, or actually the actual final frame, it's not necessarily the visible frame, when you're finished with a single frame. And again, we call it a frame counter because if you take a look at this figure, you're actually going from basically you're scanning a whole frame from beginning to end. That's why we call it the frame counter. So taking a look at the code, it's really straightforward. It's a couple of counters, and these here are basically just some registers. What matters is the following. So it only increments. This is for the horizontal counter, the HC. It only increments it when increment is asserted, and it's just a modulo H max, which is going to be 800 eventually. However, the vertical counter, as you might think about it this way, so whenever you finish a line, you increment the horizontal line. Whenever you increment a line, you increment the vertical counter, whenever you increment it. So it doesn't only depend on the ink, you also have to be at the very end of your horizontal. So because it has to be a little bit slower. Remember, it's like at the very end of this, you only went through basically one round between 0 to 525, while you went through many of them from 0 to 800 for the horizontal, because you're going left to right, 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 all the way through. And that's pretty much it. That's how that counter is. And again, the frame start that basically tells me whenever I'm at the 0 0 location, and the frame end tells me whenever I'm at the very end of my counters, both of them in here. And that's basically the frame counter. So what does the decoding circuit do? Remember, it's like that. Now we just talked about that frame counter in here. What does the decoding circuit do? It actually tells me where you are in the HC and VC, and actually generate the H sync and V sync and the video on. So let's take a look at how it actually does it. Again, I'm just repeating, it's the same basic figure. So we have generated these numbers. And let's take a look at the H-sync. Well, if you take a look at the H-sync is 1 except when it is between 655 to 751, which is these two numbers in here. And the V-sync is basically in here. If you take a look at it, it's only 0 if it's between 490 to 491, and that's only it. So the decoding circuit will just take the H-sync or it will take just the H count and the V count in here, the HC and the VC that we just saw on the frame counter. And it will just basically generate these it will just generate a bunch of ones and zeros. And if you think about it also with the video on, it should only generate a video on signal during a displayable region, and this displayable region for the horizontal, it has to be between 0 to 639, and for the vertical, it has to be between 0 to 479. So let's see how this is actually implemented. So this particular code in here implements the whole system from beginning to end, but what I care about for now is actually these numbers. So we just program all of the numbers that you see on the figure, all of them between the retrace and you can read them on your own. It's just basically program them as local parameters so that we can change them. So if you have a little bit of a different screen, you can actually go in here and play with these numbers. If you have if you see some sort of a black border in your screen. Also, we're gonna, if you take a look in here, we have an instance of the frame counter, and then the H-sync is just basically, it's testing that particular here. It's actually testing, are you between 651 and 751? And it's just doing it with using the parameters so that it's a little bit more generic. If that's the case, you're actually outputting a 0. The same goes with the V-sync in here, and it's actually also testing like these two conditions, and these two conditions will yield where if you are between 490 to 491, I believe, if you're between 490 and 491, you should be at 0, and that's basically, these are the V-sync and the H-sync. And then you take a look in here, we have the Q register, and this is basically just to generate a tick at 25 megahertz, because remember, it's like, it has, like, you have to move these counters at the 25 megahertz so that you get the clock rate, the pixel clock rate, not the system clock. So we have that, and we're going to connect it to the With the frame counters, this is actually the increment. We're going to just connect it to the increment in here. And that's pretty much it. The rest of it is, if you take a look at it, I'm just basically saying if the video on, basically if the video is within these two green signals in here, I'll basically connect. Remember, it's like it's connected to a multiplexer. This is basically what's implementing. It's implementing a multiplexer. If it is on, I want you basically to pass the input data all the way to the R and the G and the B. If not, you just basically at 0 because you are black basically when the display is off. Basically, you're in one of the borders. And it's registered just to avoid any glitches. So technically, if I take this particular code and I just connect the input, which is VGA SIRGB, okay, if I just connect this particular input to switches, okay, to exactly 12 switches, I should be able to display solid colors on the VGA. So let me show you that. So I went ahead and generated the bitstream and loaded it to the FPGA. I connected it through a VGA to this particular monitor in here, which is also a VGA monitor. And I also connected the VGA serial in RGB to 12 switches, because remember, so we have 4 bits for the red. These are the first 4 bits in here, and then I have 4 bits for the green, and then I have 4 bits for the blue. The program is currently running, and if you take a look at the screen, it's actually 0 because all the switches are at 0, and that's actually the black color. So if I actually start changing the colors a little bit, so I don't know if you can see it in here, I started to get the red, and this is basically the brightest red we can get because I set them all to 1. I can change the brightness of the red. Again, it's just a solid color. The camera might not be showing you all of them, but it's actually just changing how bright the red is. I can do the same exact thing. I'll put them back to zeros for the green, for example, and I can show you this is basically the brightest green we can get. And the same goes with the blue, and in here I can basically get that. And I can get any sorts of combinations of colors, so I'm actually just changing these switches in here, and you can get, like, it's actually, you have 4096 of these colors, and it all is based on what switches you actually turn on, what switches you turn off. Basically the combination of the red and the green and the blue.